Welcome to this video on solving nonlinear equations. So in this video we will talk about how to find roots of nonlinear equations numerically. Eventually we will do this with SciPy.optimize, which is a fast and safe choice for doing so, but we will also build our own algorithms to sort of understand how that can be done and what happens underneath. So I will be importing NumPy and some plotting tools, and then I will import linear from SciPy and optimize from SciPy as well. So why are we doing this at all? In economics, we really like setting first order conditions to zero. We basically do that every time we want to solve for optimal behavior. That implies that we get a nonlinear equation on the form some function f of x is equal to 0, where we start from x being just one real number. We will talk about the multidimensional case later. So if you stumble upon such an equation, you want to solve it numerically, there's generally sort of two types of methods. Either you can use derivative-based methods. They're the most robust, they take the fewest steps. But there's also something called derivative-free methods, which don't require the gradients and are therefore easier to implement, though they, theoretically speaking, might be numerically less stable. But we will have a look at both of these types of algorithms below. As an example, we will use this simple polynomial which we want to find the root of. So in terms of derivative-based methods, the basic method here is Newton's method. And let's start by saying that we use the first order Taylor approximation of the function at a new point x1. So let's say that we know the function at x0 and we know the derivative at x0, then the first order Taylor approximation is just this linear function here, and this is now the function value at x1. Now the idea is that we will choose x1 such that the Taylor approximation is 0. So we set this equal to 0 and we derive what should x1 be in terms of x0. So now we have an expression for how to sort of update our initial guess to a new guess. And that's we simply build an algorithm to do that. We say, let's choose a tolerance, a small positive number. Let's guess on some initial x, and let's set a counter equal to 0. Then we calculate the function value and the derivative. And if the absolute value of the function is less than 0, then we're happy, we just stop. Or otherwise, we calculate our next guess using the formula from above. Then we increment the counter, and we return to step 2, and we continue until this works. So now we have a function for implementing this in Python. So we take an initial guess, we take in a function, and we take in a derivative function. So that these are callable, so they can calculate the function value and the derivative based on our current x. Then we set a maximum number of iterations, we set a tolerance, and we have a boolean here for saying whether we want to return full information or not, which will sort of be used for plotting what's going on. We start by initializing some lists where we will store information on what's going on, and then we sort of begin the real stuff, where we set our x in this period here equal to x0, and then we set our counter equal to 0, and then we begin our process here. So we say that our x, that's equal to our current xk, we calculate the function value, we calculate the derivative, we store all this information, and then we check whether our function value is less than the tolerance. If it is, then we break. This is a while loop, so it will continue until either we meet this tolerance or our maximum number of iterations is if we come above that. If we don't break out, then we do our update step and we increment the counter, and things goes on in this way. Once we are out of the while loop, if we have full information on, then we will return the vectors of everything that we have done. Otherwise, we will just return the function value and the number of iterations. So this is a good time to pause the video and be sure that you understand what's going on in this function and how it relates to this algorithm. Okay, I hope you have done that. Below here, there's a function which sort of plot the convergence. I will not talk about that in detail, but we will use it to understand what's actually going on. But let's take our example here. So I have plotted in the function and the derivative, which I have just taken by hand. And if we run this, then we can see that we get out a solution 4.4 something. It took 7 iterations, and we can see that in And actually the function value is very close to 0 at this point. So we have found a root of the function. So let's try to understand what's actually going on here. So if we plot our function and we think about our initial guess, our initial guess here was set at some point here as -5, and then we are saying, okay, this is our initial guess as -5. What is the function value there? And then we do the Taylor approximation, so that's the linear line here, and we project that, okay, now I should guess that our root should actually be here. So then if we take a step forward, then we can see that now we guess there, but we see that, okay, the function value is not 0, so we do the Taylor approximation again, and we have a new guess. And we can simply continue by doing this, and we can see at some point we actually overshoots and gets on the other side, but then eventually we converges into our solution. So that's basically how the Newton method works. You can play around with this a bit yourself and try out maybe some other initial values or similar if you want to understand it in more detail. Okay. One thing that we used here is that we used this derivative here. So we actually had a function for calculating the derivative. Sometimes this might be hard. So you can actually also just use a numerical derivative instead. So here the idea is that if you know the function f, then you can define the numerical derivative as a sort of an approximation of the real derivative, where you just take a step from in the x, and you take the difference for the initial value, a function value, and you divide by the step size. So here I'm setting a step size of 10 to the power of -10, and now I'm doing my approximate derivative here based on my f function and this step size. And then I can do my find root function just with this approximate derivative instead. And you can see that it works. In the same number of iterations, we find the root and we find the function value. Now you might wonder what happens if we change this step size here. And here it sort of suggests that I could try to set the step size to 1. So let's see now what happens if I do that. It actually still converges, but it takes a lot more iterations because this is imprecise. If we choose something in between, then it might be okay. This actually this was just like this. This actually seems to be okay. But typically doing something like 10 to the power of -8 is a good idea here. If you do it too small, then sort of numerical error can create problems. So around this is a good thing. Okay, let's just also try another example. So here I have a g function that's the sine, and the derivative then is cosine here. And now we can see that, okay, we guess on 4 to begin with. That's not 0. We do our Taylor approximation and guess where the 0 is. And if we step forward, then we can see that we converge to something. Now, what happens if we instead choose the initial value -2? We set that in here. Then you can see that's also not 0, so we have an update step. And you can see that now again we converge. But note that we converge to a different 0 than before. Here there's many zeros of this function, and our methods only ensure that we converge to the nearest in some sense, or at least a nearby root. So that's always something you should be aware of, that this is a danger. Okay, now let us turn to derivative-free methods, and especially let us look at the bisection method. This is simply another way of finding a 0 for a function without doing the derivative. So let's just start by plotting the function. And then the basic idea is that if you know the function value at a and at b, two different values here, and you know that it's positive at a but negative at b, if it's a continuous function, then there must be at least one root in there somewhere. Then the idea is to say, okay, let's start by saying that our A0, that's the A we guess on, and B0, that's the B, so the bounds here. Then we assume that they have opposite sign, the function values. Here it's positive and negative. So if you multiply them together, then it's a negative number. Now we compute the function value at the midpoint, where we divide, simply take the sum and divide. And then we determine the next sub-interval we want to look at by looking at these signs. So if A and M have different signs, then we will set our A equal, we will keep our A, but we will update the B to the midpoint. So now we focus on the range between A and B, A and M, because we know that this is two numbers with different signs. Otherwise, if this is not the case, then we will look at M to B, because now M and B will be opposite signs, and we will repeat this until our function value at our M here is less than intolerance. And this is actually right. If we should do this completely right, then we should take the absolute value here, and we should also call it K as we did above. Okay, so let's look at an implementation of this. So we have our function, we have some left and right bounds, we have our maximum number of iterations, we have a tolerance, and we have again sort of something for where if we want to have the full information come out of this. Okay, I think that's all we need. And then we start by testing the inputs. Are they, if they are of either them are 0 or or they have the same sign, then we say we cannot do this. Then the bisection method fails. Otherwise, we initialize our list of what's going on, and then we implement our algorithm. So the midpoint, that's simple. We take the function value at the midpoint. We store all the information that we have. If our absolute value is less than intolerance, then we break out. Otherwise, if we have that the A and the M have different signs, then we set B equal to M. If B and M have different signs, then we set A equal to M. And if none of this is fulfilled, if something weird has happened, then we say that this is failed. We increment our counter, and we return everything if if we need that, or we return our midpoint and the number of iterations. Here I did it in slightly different way in terms of using the while loop. Now I did a while less than max ether here. That's just another way of implementing this maximum number of iterations than what I did before. But okay, let's just run this, and here I did it between 2 and 7. I think I could do the same thing as I had above, and it's this converges nicely to results that very similar, and where the function value is close to 0. There's a trade-off between more iterations. Before we had 7 iterations, right now we have 33. But on the other hand, it's easy to implement. We don't need any derivatives. Again, this is a good time to pause the video and spend a bit time on what's going on in this function and how it relates to this up here. Otherwise, let's have a closer look at what happens graphically. Again, there's a function here for doing the graphic analysis. We will just take that as given. And then let's see what actually is going on here. So we can see that our initial bounds here are -8 and 8. And we say that, okay, this is a positive, this is a negative. Let's take the midpoint, that is at 0. And there we have a positive value. So now we know that it cannot be in this left part here. That cannot be where the solution is, because this is a positive and a positive. So we take one step up. Oh, sorry. We take one step where we simply close down the first part of it. So now we're looking in a new direction. We see this is again a positive, so we need to again take it in that direction. Now we get a negative, so now we need to move in from the other side, and you can see that now the bounds get smaller and smaller and smaller, and actually rather quickly. We found a rather good solution, but then it takes a lot of iterations before we get to sort of below our tolerance. That's generally true for non-derivative based methods, that they can sort of have a hard time actually converging. Okay, so this was a derivative based example and a derivative free example of how you can implement a equation solver. Okay, now let's look at what we can do in SciPy. As I said, they have better implementations, so use those in practice, but it's good to understand how you could do it yourself. So we can use root scalar in this case. We just give it our function, we give it our initial value, we get it our derivative function, and here I explicitly say that I want the Newton method, and we get out the results as we had before. You can see it takes 16 iterations, and it counts that it sort of does 32 functions calls, because it also needs to call the derivative. If you use the bisect, then you can see that it takes more iterations, but it doesn't take that many more functions calls, because it doesn't need the derivative. Typically, for one-dimensional cases, the best choice is sort of Brent's methods, Brent Q, which sort of is often where we find something that converges the fastest. And it actually just, I don't know why I put in maybe let's do the exact same intervals. It actually didn't change much here. But anyway, sort of this is typically what sort of how it's done. It's done the best. Okay, so this is how you can do it in one dimension. Now let's talk about multidimensional stuff. So let's consider solving nonlinear equations on the form where now x is a vector of real numbers. And for some specific example, let's take an h function here, which looks like this, and has the following Jacobian down here. This is just a weird example that I have chosen. So let's set that up. Now we can use Newton's method again. We use the exact same strategy as solving one equation, except that now we will be working with this Jacobian instead of a single derivative. So now the update step is that our next x here, that will be our x now minus, and then our function value times the inverse of the Jacobian. Maybe to be, now I call it n, before I called it k. So let's just update this such that we are sure about that there's no difference here. Good. So this is just the same update steps as before, and therefore also the find root multidim looks very similar. It's the same types of inputs. Now there's an extra bool here about whether we will use linear solve in our update step. I will mention that briefly. So we initialize, set x equal to our initial guess, we initialize our counter, and we iterate while our counter is less than or equal to the maximum number of iterations. We calculate our function value and the derivative, and if we have that our maximum absolute value here, and now this doesn't make sense, there's only one, I don't know why, that's just a mistake. If just the maximum, so just the absolute value of the function is less than the tolerance, then we break out of this. Otherwise, we do our upstating step as long as use solve is equal to 0. We can also think about what we're doing here as solving an equation system, and in that case, we will write our update step as this. There are sort of numerical reasons why this might be a bit more stable, but we will see that they get the same results in our case. We increment the counter and we continue. Again, this is a good time to pause the video and understand what's going on in this function in relation to the text up here and the original algorithm. But let's try to implement it in practice. We guess on 0.0 and we run it. And now, okay, there was actually, I thought there was no reason for the all. So even though this is only one number, because this is a number array, then we actually, okay, one thing we could do is we could do it like this, I guess, because there is only one value. Let's see whether this works. Now this works. I think this is nicer than the all, because the all thinks about this as a vector and it's really just a number, but it's just a number array anyway. So therefore, yeah. Okay, so now this works, and we can also see that we can do it with use solve true on, and we get more or less exactly the same result out. That's a small difference, but they're really, really small. Okay, so in that case, it's actually almost as easy to solve a multidimensional problem, even though it looks complicated. Numerically speaking, it's more or less the same as the one-dimensional stuff. So that's nice. Of course, you can also do this in SciPy. There are many different algorithms for doing that. This default in SciPy is something called Hybrid. I will not talk about what that is exactly, but you can simply use the optimize.root, and you can either solve the problem using the Jacobian explicitly, and you can see that we find the same solution as we had up here, or you can do it without the Jacobian explicitly, and it will then use a numerical approximation of the Jacobian instead. And you can sort of see here that it's here up using it's using one evaluation of Jacobian and 10 function evaluations, while down here it needs a bit more function evaluation. So sort of there's always a trade-off there. That was all for this video.